MeshViz is a complex simulator for a resistive network and its elements. It is part of a larger collaboration with teams of engineers at the Robert Gordon University and the University of Aberdeen. The RGU team is working on creating meshes made up of resistors. These will be placed around oil pipes underwater. If the pipes get corroded or malfunction in any way, the current passing between the resistors will change. This will signal to the engineers working on the oil rigs that the pipe is defective and where the breakage is located. Without these meshes, companies have to send divers to manually check miles of pipes to locate the breakage. Being able to find the breakage as soon as it happens means that the repairs can take place almost immediately. The oil that would have otherwise leaked into the sea can be contained, and this can not only save money for the company, but, more importantly, stop the oil from contaminating the sea and polluting the environment. Our team, at the University of Aberdeen, developed a simulator for these meshes. MeshViz allows the visualization of the meshes and their resistors, as well as the simulation of pipe breakage and resistivity changes. So, how does it work? MeshViz uses a database to store nodes and resistors making up the mesh. They are connected to each other and have properties such as length, resistivity, and material. The core algorithm of MeshViz goes through these resistors to calculate the total resistivity value between any two nodes. This was achieved through the use of Python-free, SQLite, and various external libraries. Let's have a look at the interface. All you need to do to start using MeshViz is download the exe file and open it. We generate a new mesh from a pre-existing layout. We select width, length, and type. We can either create a new resistor type for this mesh or select a pre-existing one. By clicking on Tools and then Validity Checker, we can confirm that the mesh is valid. We can grab any node and move it around to change the visualization of the mesh. We can also disconnect a resistor and reconnect it elsewhere. We can also edit the resistor's length, material, and its resistivity value, and even its color, to be able to distinguish between different types of resistors. By clicking on Tools, then Resistance Calculator, we can select any two nodes on the mesh and calculate the resistance between them. We can easily delete some of the resistors from the mesh and see the resistance change in real time. Let's now create a new mesh on a different tab. We can create it from scratch. We can create a new material and generate some new resistors. As we add new resistors to the mesh, we can move them, connect them, and recenter them as needed. By enabling the opacity, we can visualize the different meshes of the project as if they were stacked on top of each other. To simulate a breakage, we can set one or more resistors to broken. The resistance calculator will show the change in resistivity, signaling the fault in the mesh. Once we are done with our project, we can save it and load it again later on. MeshViz was designed with the idea of creating a simple solution for a complex problem. While the core algorithm, as well as the calculations performed, are quite complicated, the user interface is simple and very intuitive. This allows everyone to get the best out of this application. MeshViz has multiple key features that set it apart from similar applications. It is a cross-platform software and is executable on most of the major operating systems. It allows the user to choose among multiple predefined mesh layouts, as well as create new mesh layouts from scratch. It allows the user to specify two nodes and calculate the equivalent resistive value between the two. It also lets the user simulate fault scenarios of the mesh elements and see the resulting effects on the mesh. MeshViz was constructed with security and stability in mind. By choosing the hexagonal architecture, we made sure user errors are eliminated and data integrity is not compromised. The design choice of using a data-centered architecture allows the program functionalities to be modified and improved in further versions with little modifications to the existing code base. This provides a stable and reliable platform for engineers to use in their research. The core algorithm of MeshViz iteratively simplifies the circuit by either removing a resistor or a node until only one resistor and two nodes remain. It does this by using known equivalence formulas, which serve to simplify the circuit whilst keeping the overall resistivity the same. The resistivity of this final resistor will be returned to the user as the equivalent resistance between the terminal nodes. Our team was already familiar with most technologies used in the development process of MeshViz, which allowed for a smooth learning curve and ensured efficiency in our project. Using our own machines to build the system eliminated the issue of hardware accessibility. We finished the project in the expected timeframe, thanks to following a preset schedule and dynamically adapting it when necessary. For every mesh that needs simulating, MeshViz can offer a wide range of possibilities and features. It will handle all the complex calculations instantaneously, allowing the user to focus on more important problems and facilitating the creation of better and more efficient resistivity meshes.